Good morning, Earth Science students. This is Mrs. Anderson for my final sign-off today. This is my last day of student teaching, so that's why we've got all the sad gifts today. All the sad, nerdy gifts from all of the nerdy things that Anderson has referenced over the time. So it is our last day together, but if you are at home right now, so you won't be doing the Lucky Bucket, but we're still doing the Lucky Bucket. Today we are wrapping up Kepler Lab 1 and probably starting 2. There is an Edpuzzle that's due today, so if you are at home and you have not showed me your lesson review yet, you could take that Edpuzzle and then just show us your completed page 73 when you get home. Remember, if you don't have your book, the digital copy is linked in Google Classroom right at the top, so you can access that. So we will take our Edpuzzle, we will do our lesson review, our homework check, and then we're going to hand out a new study guide. And we are going to show the things that you could have answered already. So we've talked about the solar system, planets, moons, astronomical unit. That was all in your lesson review. We have our tentative date for our test as May 9th. This could change a little bit with MCAs and the shortened periods. For example, it's taken us 3 days to get through the first Kepler lab, which should usually take like one class period. So this is subject to change, but this is what we're planning it for now. You could also define gravity. You could also describe how changing the mass and distance in objects can affect the force of gravity. You could do geocentric, heliocentric. And then our learning target today is that I can explain Kepler's first and second laws of planetary motion. So we talked the last few days about how Kepler's first law indicates that our planetary orbits, all planets follow an elliptical orbit. An ellipse is kind of like a flattened circle or like an oval. So all planets follow that. And actually, Johannes Kepler, noticed the first law of planetary motion, or the second law of planetary motion. He noticed the second law first, and that helped inform his first law. Who knows why he decided to order them the way that he did? But we'll talk about that today. So Kepler's second law, you can find that on page 54. And what that means is that the orbits, wherever you're at in the orbit, it sweeps out equal amount of time. So if you're at the farthest end, the side of the ellipse that is farthest away from the sun, you're going to slow down. And that period of time is going to actually cover the same amount of time, though, because you're traveling a smaller distance, but slower. That's going to be the same amount of time as when we travel a greater distance, but faster on the near side of the sun. So we will watch a video explaining that in a little bit more detail. We will revisit our first law, our lab yesterday, where we made our eccentric orbits, or we were measuring eccentricity, and we made our elliptical orbits. So we are measuring the major axis. So here we can think about the axis of a graph if you're making it in math. We have an axis that is longer. Our x-axis, here, is longer than our y-axis up and down. So our horizontal axis is longer, so we call that our major axis. Think major as in bigger. The minor axis is our vertical axis, so up and down, minor being smaller. So our major axis is measuring the distance or the diameter from one side of the longest side to the other side. So we are measuring that. We are dividing that by the distance between the foci. That's the two pins that we had yesterday. So you're dividing that by the distance between the foci, and that's going to give you your eccentricity. So the eccentricity of an ellipse tells you the shape of the ellipse. So if the number is closer to 0, your ellipse will look more like a circle. And if your number is closer to 1, then your ellipse will look more like an oval. So yesterday we noticed that our distance between the foci, when they were the farthest apart, that then gave us the number closest to 1. So if you were measuring the distance of your major axis, then that was, for a lot of people, around 11, 12 centimeters. So 11 divided by 12 is going to be closer to 1 than our 3 centimeter foci, because remember we had our 11 centimeter string, so there was a lot more slack with the 3 centimeter ellipse. So that made a larger elliptical orbit, made a larger ellipse. So then that was your larger number. So then that was like 3 divided by 20 or something like that. So that's going to give you a number that's closer to 0. So we would say that the most eccentric orbit, or the number closer to 0, is more like a circle. So that would be our ellipse that was, our 3 centimeter distance between foci. And then our ellipsis, or our eccentricity, was higher with our elliptical orbit when it's farther between the two foci. So we're thinking about the planets closer to the sun as having a more circular orbit, and the planets farther away from the sun having more of that elliptical orbit, or more oval shaped. So we're going to give some time to answer the questions on the very back of the first lab. We'll go over the answers together. We're going to save it, and there will be a 20-point summative lab quiz next Tuesday, depending on time here. It might get pushed further out. We'll start then Kepler 2. So the second law, again, we talked about how the planets speed up as they orbit the sun, and then they slow down as they get farther away from the sun. So we will have some pre-lab questions. We'll have a hypothesis that the planets change speed because. You guys will have your hypothesis, and we'll need some grid paper and a highlighter today. So you don't have these materials, so at home, you might not be able to do this. If the items are in Google Classroom, you can certainly try, but we can always just get you caught up when you return home. So we will have this grid paper that's going to show us the elliptical orbits, and it's going to show us the different fragments of time. So we are going to try to prove that the orbit sweeps out in the same amount of time. So what should happen is that this triangle, we're going to count the amount of squares here, should be the same as this triangle and this triangle. The area, or the amount of squares, should be the same. And why that is that as a planet approaches the sun, it's actually going to speed up, because if we don't speed up, the gravity, or the mass of the sun, is actually going to suck us in. So the way that we overcome the immense gravity is we have to speed up. So then we speed up here, we resume normal speed here. And then if we take this corner too fast, we talked about this a few days ago, if you take a corner too fast in a bus, you're going to fly off, because your body's going to want to keep going in the direction that it's currently moving. So we have to slow down so that we don't sling off into space. So we slow down here as we make the curve, and then we come back around. And these areas should all be equal. So we will highlight these areas today, and we're going to number them off, like 1, 2, 3, 4. We'll count them off. And then that should prove our hypothesis that it is the same. So we think about this like a track, and I'll kind of bring in some of my college track experiences. And those that are in track know that the runners, they start at a staggered start. So if you're making a lap, if you're running a 400 meter, so a quarter mile, if you're running in a race, 400 meter, you're going to start at different spots, because the route, the closest route, is actually a shorter distance than the farthest route. If you all started at the same starting line here, the person on the outside would have an unfair advantage, or they would have an unfair disadvantage, because they are going to be ending up running more distance here. So that's what we're looking at here as well. The planets on the inside, they have less distance to travel than the planets on the outside. Lastly, this is just an animation of how fast the amount of time that the Earth spends in each one of these portions of the orbit. So we see that the greater period of time, this is a faster period of time here. So we see that the planet moves a lot quicker when we're closer to the sun than when we're farther away. That time we slow down, and those increments are much smaller. That's probably about as far as we'll get today. The rest of this we'll probably have to tackle on Monday. But you stay safe, stay healthy, and we will see you on Monday when you return. If you have any questions, feel free to email Mr. Payne or myself, and we will see you when you return. Have a great day and be kind.